Welcome, ladies and gentlemen, to Integrated Math 2. In today's episode, we will be discussing Chapter 1.3.4, which is Angles and Sides of Triangles. So to begin this lesson, we're on Section 104 here. And we will be, actually for purposes of this video, we're going to be skipping A through C. That's just a bunch of group work designed to get you to find a pattern of angles in the triangle. What it really culminates into is how to do Part D, which is something that you guys may or may not be exposed to, and that is ultimately that the sum of the interior angles of a triangle always sum to 180 degrees. So actually I'm going to write that down before we even begin what we're about to do here. The sum of angles in a triangle add up to 180 degrees. 180 degrees. Now some of you guys may know that. If you don't know it, it's not a big deal. Some of you may know it and know why. Some of you may just have heard someone say it and therefore it became part of your common knowledge. But we're actually going to prove this idea in this lesson. And I'm going to use this diagram to do it. This triangle with the DBE and the AC. So in order to prove this, we're going to go back to what we know about parallel lines, right? Again, notice the markings. That means that they're parallel. Well, what I'm going to do is I'm going to establish a couple of things real quick. I'm actually going to do what's called a two-column proof right here, where on the left side I'm going to write the statement that I'm going to make, and on the right side I'm going to write the justification, or some people write down what's called the reason, right? Why I'm able to make such a claim. Well, from here I can actually just begin by saying that angle D plus angle B plus angle E is equal to 180 degrees. How do I know? Well, that's because this is a straight angle, right? It's a straight angle which sums to 180 degrees. We know that to be true. It's ugly. Straight angle. Okay, so from here, what else do we know? We know that, and in fact, I'm going to go ahead and just relabel this. I'm going to call this line L and line M. And I'm going to go and say that line L, so L is parallel to M. And actually that's one of our good old buddies. That's actually given. And again, it's given because the arrows were given to us, right? And so now from here what I'm going to do is I'm going to use the consequences of parallel lines being cut by a transversal. So from here, if you look at the transversal going down and to the left, or rather going up and to the right if you read it from left to right, we can say that angle D is congruent to angle A. How do I know? Well, look at where angle D is and look at where angle A is, and maybe even look back to your notes about parallel lines and the angles that they create. These angles are known as alternate interior angles of parallel lines. Now, knowing that, we can probably go and make another assumption here, and that is that angle E will be congruent to angle what? Take a few seconds to guess. If you want to pause, go ahead. You should have guessed angle C. Again, for the same reason, alternate interior angles. And so because we know that these angles here, and I'll even highlight them in blue, these angles are congruent and these angles are congruent, what I can do, in fact, I'm going to highlight those in a different color here. I'm going to go and call these in purple. Because they're congruent, or because they're identical, I can make a substitution. Instead of angle D, I can say that this is angle A. And then I can say, instead of angle E, I can say this is angle C. And of course that angle B, was always there, and because I just did substitution, right, I can say, all right, well that's going to be the same thing as angle D plus angle B plus angle C. Right now I can call that substitution, which then if I can say that D plus B plus E equals 180, that means that angle A plus angle C plus angle B must also equal 180. And that is how you know for sure that the sum of angles in a triangle add up to 180 degrees. Now again, you were supposed to do a bunch of group work to kind of guess or have some kind of intuition that this might be true, but part D is to verify that the statement is actually true. We will put this into a resource page when we get a chance, or a graphic organizer, or like a theorem graphic organizer, and then we'll go from there. I'm going to pause real quick, grab the next problem, and then we'll be right back. Next up is 1-105, which is the triangle inequality conjecture. It says, now that you have the triangle angle sum theorem, you can always determine the third angle measure of a triangle if you know what the measures of the other two angles are. Is there a similar relationship among the side length of a triangle? That is, if you know two side lengths, can you determine the length of the third side? Okay, so we're supposed to discuss this in our groups, but basically what I'm going to do is I'm going to use this diagram over here. Notice how it says that we have side CB being 8 and side AB being 6, right? And so what I'm going to do is I'm going to go ahead and call this question mark, I'm going to go and call him X, and we're going to go and find out what is the range of values that X could possibly be that would allow this shape right here to be a proper triangle. So here's what I'm going to do. I'm going to draw that figure down here again, and there is a Desmos tool for this. I'm going to go a little bit old school, and hopefully that's not too confusing. Oops, darn it. And we'll see how this pans out. And so from here, what I'm going to do is I'm going to find out just how short this angle could possibly be. Okay, so, or rather, just how short this side CA could possibly be. Now, if I want to create the shortest side possible, what I'm going to do is I'm going to take these two parts of the triangle and I'm going to close them up. And when I do that, hopefully you have enough imagination to see this. This point here, when I close up this angle, this point on C is going to migrate over to this side. Imagine as if I'm closing a book this way. So what happens when I decide to close this book? Well, what's going to happen is that this C is going to overtake, right, because he's longer, he's going to overtake the length of BA. So again, BC is going to overtake the length of BA. And what I'm going to get is I'm going to get a singular line segment right here called B, and then the A would be here, and then C would be here. So remember, the length of BA was 6. So what I'm going to do is I'm going to say, well, what is the length of this AC here? Well, remember, if BC is 8 and AC is 6, and I close BC over, what does that leave me with a length of for C? Well, what that leaves me with is it leaves me with a length of 2. So what does that mean? Well, it means that the X value definitely has to be bigger than 2 in order for this whole thing to close up appropriately. It's got to be at least 2 in order for that to happen. Now, what if I went the other direction to find out how long this thing could be? Like, what's the biggest distance I could have? Well, from here, that's going to involve, and I'll go ahead and draw this diagram one more time. Instead of closing the angle, I'm actually going to open the angle. I'm going to open this book so that it's completely straight across, going this way instead. And so from here, I'm going to put the 8 down and the 6 here. Now if I open this up, now if I take this side C and I push him down towards there, I'm going to end up creating a line segment right here where this is A, and this is C, and this is B. And in totality, this whole thing would be an 8 and a 6, which would be 14, which means the most I could possibly be and still stay one within this line segment right here would be 14. So that means that the X value, this value here, has got to be not only bigger than 2, but less than 14 at the exact same time. So the way the generalized version of this works is if you have, and this is the triangle inequality theorem, that is, if you have a triangle with side lengths A, B, and C, if we did it from the perspective of C, C would have to be larger than the difference of the sides, but smaller than the sum of the sides. Okay? So let's write that down. The third side of a triangle must be larger than the difference of the other two sides and smaller than the sum of the other two sides. And that's what that inequality is saying. We'll do a couple of examples of this, and then we will rock and roll with the next theorem. Give me a second. All right, here are some example problems right here. Now remember, the third side of a triangle is always going to be smaller than the sum of the two sides, but bigger than the difference of the other two sides, okay? So if we look at number 1 here, it doesn't really matter which side you pick. I'll go and choose 10 as my third side. Is 10 in between 5 plus 3 and bigger than 5 minus 3? Well, this part's definitely true, but 10 is definitely not less than 8. So I don't believe that number 1 will produce a triangle, so not a triangle. Number 2, again, I'll go and just choose 9 as my third side. So is 9 less than 4 plus 12 while simultaneously bigger than, I'll go and just do this backwards because we don't want to have negative sides on a triangle, 12 minus 4. Okay. Is this true? Well, this is 5, 9, and 13. This one is a winner. 2 will be a triangle. Yes, triangle for that one. Number 3. So again, it doesn't really matter which one you choose. I can go ahead and choose 2 if you guys want me to. I'll go and just so that, to keep things random. Is 2 smaller than 5 plus 4 while simultaneously larger than 5 minus 4? Well, is 2 smaller than 9 but less than 1? I think that is true. So this would be yes, triangle. Number 4. Again, I'll just go and choose 3, right? 3. Is 3 smaller than 5 plus 8 but larger than, say, 8 minus 5? Well, here it looks like we got a winner. 3 is definitely less than 13, but is 3 necessarily less than 3? I don't think so. This is no triangle. So that's how the triangle inequality theorem works. Those are your 4 examples. I'll be back with the last thing. And lastly, we have 1-106, which is basically trying to link the idea that when you have a large angle, it will be opposited by a large side. What does that mean exactly? Well, if you compare, if I compare these two triangles right here, if I do A, B, and C, this, and I do this instead, again, A, B, and C, clearly the BC on the right side is a larger side than the BC on the right side. Now, is it just happenstance that this angle here, this angle for A is small, and this angle for A here is large? I don't think so. It should make sense that the wider the opening of the angle, the more triangle you're gonna need to fill the gap on the opposite side of that angle. So, when it comes down to longest side versus largest angle versus medium side, medium angle, small side, small angle, bottom line, they correspond. The largest angle will be opposite the longest side. The medium angle will be opposite the medium side, and so on and so forth. In fact, I'll type this out for you guys. In a triangle, the largest angle will always be opposite the longest side, and then the medium angle will be opposite the medium side, and the small angle will be opposite the small side. Again, think of the opening of the mouth, right? If this mouth opens wide, there's a lot more triangle that needs to be used to connect them. Feel free to copy that down. You were supposed to discover that in parts A and B right here, but let's take a look at question C here. We've got a triangle A, B, and C, so let's check this out. So it says if we do A, let's see, B, and C. So it says AB is worth 10, BC is worth 10. Obviously, it's not drawn to scale, but that's okay. And AC is worth 12. Which angle is the largest measure? Well, remember, this is the largest side, right? So the opposite angle will be the biggest angle. And again, it's not drawn to scale. I apologize for that. In fact, why don't I go ahead and redraw it so that it is to scale? If this is, say, like this, 10, 10, and 12 like that, this would be a 10, this would be a 10, and this would be a 12. This would be B right here, and this would be A and C. So again, the opposite angle to the 12, which is the longest side, will be the largest angle. So we would say angle B is the largest. Angle B is the largest. So let's try it again here. Oh, I accidentally did D on accident. Let's do part C real quick. Looks at 4, 9, 12 triangle. Let me go ahead and delete some of this stuff here. Go and delete some of this stuff here. Get some space going. And so from here, we've got another triangle. I'm just going to call them A, B, C. So A, B, C. So AB is 4, BC is 9, and AC is 12. So that's A, B is 4. Let me see. BC is 9, and there we go. All right, so which angle has the largest and smallest measures? Well, where's the longest side? The longest side's the 12. He's got to be opposite the angle B. So you would say angle B is the largest. And then the medium one would be A. So angle A would be medium. And that means that angle C is the smallest. And again, wide mouth, the more triangle it takes to connect the two ends. Smaller mouth, the less triangle it takes to connect those ends. And that's pretty much it for this lesson when it comes to triangles. You will be getting a resource page, or you can download it and fill in the theorems, especially the triangle angle sum theorem, the triangle inequality theorem. Make sure you have that down. And then this guy. If you have any questions, feel free to leave them in the comments. Otherwise, I will see you in the next episode.